All right. So in the last class, we had an introduction to this course, and also we started to make a review of some prerequisite knowledge for this course, including the general knowledge about power electronics, including the basic concepts in terms of control theory, okay, including modeling and control. That was very brief review. I said in the end of last class that it would be useful for you to maybe take a look at your undergraduate textbooks on power electronics and automatic control theory. And then you can have a better preparation for the following discussion for this course. And today, I'm going to continue with the review, maybe again, some basic but very important concepts. Start with these very important concepts. But then I would like to spend some time on maybe review together with you on some mathematical tools that we have already learned before, and will be very useful in your future career, actually, I would say, in terms of the fundamental tools that we used in dealing with modeling and control. Okay, that's the first part of today's class. We'll review together some mathematical tools and basic concepts. And the second part is going to be the first mathematical model we're going to develop for power converters. So today we basically have these two parts. All right. We had some discussion already in the last lecture about some important concepts, including what is control, what is automatic control, the fundamental nature of control, and including discussion about feed-forward, feedback, and how to distinguish feed-forward and feedback. And in control, what are the differences in terms of performance with feed-forward control and feedback control. We also had some discussion about what is linear system and what is nonlinear system. And then the fundamental approach we usually adopt in engineering to deal with a nonlinear system is because fundamentally, or strictly speaking, almost everything in our practical world is nonlinear. But so far, the only effective mathematical tools we can use to handle are still linear systems. So in order to be able to handle nonlinear system, we have a very often adopted approach, which is called the small signal linearization around a steady state point. That was developed many years ago, but turns out to be very effective in almost every engineering area. Okay, so therefore, last time we also had a discussion about what is small signal, what is large signal. Based on the name, we could tell the difference is probably in the magnitude, how much the magnitude of the disturbance is. If the disturbance magnitude is small, then it's called small signal. If the magnitude of the disturbance in the system is large, then we call that large signal. And we can understand that in this way. But from what we discussed in the end of last lecture, we all know that fundamental nature that distinguishes small signal and large signal is actually theoretically by whether the system can be considered as a linear system or it cannot be considered as a linear system at all anymore. Okay, if it is still can consider as a linear system, and so no matter how big or how large the magnitude of disturbance it is, because it's a still linear system, then I can still consider this as a small signal disturbance because I can still adopt all the methods for a linear system. Sometimes if intuitively you think the disturbance magnitude is quite small, very often is even smaller than maybe 10% or 20% of the operating range, steady state operating range. Okay, I think 10%, 20%, that's small enough in terms of magnitude, intuitively. But if you look at the behavior of the system, and you find out that the system, even under this 10% of the operating range disturbance magnitude, the system is still nonlinear, quite nonlinear. You cannot consider this system as a linear system anymore. If you adopt linear system method, then the analysis results will be very different from the practical results. So that could also happen. So fundamentally, whether a disturbance can be considered as a small signal disturbance or large signal disturbance is based on whether the system can be considered as linear system or nonlinear system. Okay, that was the end of the last lecture. We can still go on to maybe discuss some more basic concepts. Okay. There is the discussion about the how to evaluate the performance of a system. So you must have learned this before. So can somebody tell me what were you taught in order to evaluate the performance of a system? Or from we can perform it, we can evaluate from what aspect? Nobody ever reviewed your textbook? Yes.
We can calculate the standard error and also evaluates the dynamic response.
Okay. So steady state error. But if I put it as a performance, then we usually call that a steady state performance or accuracy. Okay. And then there's dynamic performance. Dynamic response. That's the second aspect. What would you consider to be with a good dynamic response? What is good in terms of dynamic response? What is good, what is not good? The fundamental thing you're looking at is you want the dynamic response to be fast, right? You want it to be fast. There is a Euro used index in terms of evaluating how fast the dynamic response would be, which is called settling time. I think I mentioned this before. There's one, this is a very often used index. There is also sometimes other index, like this settling time is usually used to evaluate the system when it is under disturbance. Okay? There's a disturbance happens, and for how much time this system will recover to its steady state. Okay? But there is also another aspect people very often use is when there is commanding signal changing. How fast the system is going to be responding to the commanding signal changing, and there is a performance index which is usually called responding speed. Or responding time. Okay. This is the usually what we see as the block diagram for a feedback control system. This is the commanding signal or reference signal. If there is a step change, okay, of the reference signal, then you would like to see the output. This is a reference. What? The output would be sometimes looking like this. Before this point, both reference and output are staying at one specific point, and when there is a step change in reference, the output will be following the reference to another value, and then this responding time represents how fast the output is responding to the commanding signal change. These are the two performance indexes that we often use to evaluate whether the dynamic response of a system is fast enough. In terms of changing in reference, in terms of when disturbance happens. But other than this, fundamentally there is another aspect. So not just two aspects, there is a third aspect we have to evaluate. What is that?
System stability.
Stability. Stability. Because when you make a closed loop control, negative feedback control, people found out that the system, when under closed loop control, may not be always stable. Okay? It could be resonate itself, oscillate itself, it cannot reach a steady state. So there is an issue of whether the closed loop system is stable or not. That's stability. So these are the three aspects that we very often look at to evaluate the performance of a system. Okay, always these three aspects. Now, one more step. What happens if the closed loop system is unstable? So in control theory, what do we do? Don't forget, we have actually a controller. In the system. The controller, not sure whether I mentioned last time, there's also called another name, regulator or compensator. All different names, but actually they are referring to the same thing, same objective. We use a compensator, controller, or regulator in the system to redesign the performance of a system. Okay, by changing or design the structure and the parameters of this controller, regulator, or compensator, we are able to change the performance of the system in these three aspects. And first, we want to make it stable. Okay? Only when it is stable, we are able to do other designing to make sure the steady state accuracy is good, to make sure dynamic performance is good. Okay, that's the overall story. So, in general, it's very simple. Control theory, it looks like very complicated. You have, I think most of you have spent one semester to learn the control theory course. Sometimes some students may be spending 2 semesters to learn control theory. But in summary, it's very simple. What we have learned is to deal with things like this. First, to check, okay, whether if the system is already there, okay, everything fixed, okay, structure, parameter, all fixed. Then we check through some mathematical tools whether the system has good performance in terms of whether the system is going to be stable, whether it's going to be having good steady state accuracy, whether it has very good dynamic response. So this is called system performance analysis. We can use mathematical tools to find out under specific structure and the parameters of the system how well the system is performing. Okay, that's called analysis. So two aspects, two different work we want to do. One is analysis. With already known structure and parameter of the system, we are able to evaluate the performance. The other thing we do is, if you want to change performance, okay, redesign the system to a better performance system. How do you design the compensator, controller, or regulator? How do you design this? Okay, adjust the structure of this and adjust the parameters of this to make sure the performance of the system will be achieving what you expected. So this is called synthesis or design. So we fundamentally are doing these two simple things. Okay. Already known system, we want to evaluate how good it performs so that we can predict under this structure and parameter whether the system is going to be stable, how much is the steady state accuracy, and how much is going to be the settling time and the responding time. Okay, that's analysis. And the other thing is, if you are asked to design a system so that the system can have what kind of good performance, it has to be stable with a steady state accuracy of what? How much? With settling time smaller than how much time? Then you need to have a method to design the structure and the parameter of the controller. Okay. So fundamentally two things. And we have a mathematical approach. Okay. The mathematical approach is based on what we are going to discuss in the following part, based on this is called frequency domain. We have basically following frequency domain method. Okay. Frequency domain means we are basically using the spectrum, frequency spectrum of the system, okay, to evaluate the system performance and to design the controller. Of course, there is also time domain method. The frequency domain method is usually based on transfer function. We have the discussion of transfer function just a little bit later on. And there's time domain. Okay. But frequency domain is more often used. Time domain has its own benefits. Okay. We adopt it to analyze the system, but for most of the power converter system, we found out that frequency domain method is good enough. Okay, that's a rough review. Control theory, in the end, is actually dealing with these two issues using mathematical tools. I would like to leave you one more question for you to think about, but maybe I'm not going to give you the answer today, maybe sometime later, but for you to think about. I mentioned there's different names for this thing. This can be called controller or regulator. Controller or regulator, that's easy to understand because we use this to adjust the performance of the system. But then why is it called compensator? Why is it called compensator? That's a strange name. So compensate for what? Compensate what? For what purpose? You can think about it. All right. Let's again to review some of the mathematical methods. Basically, these are transfer functions and Bode plots. Transfer functions and Bode plots. Because we're going to use this very often in the following discussion. We are going to review some of the basic transfer functions we will very often use, including single pole, single zero, okay. There is also a string transfer function we're going to discuss a little bit, which is right half plane zero. Right half plane. Okay. I'd like to also discuss, let's say, combinations. When you have several transfer functions combined together, how to get the overall transfer function and overall Bode plot. Okay. Double pole. Double pole means there are fundamentally two poles. Okay. Approximate the roots of an arbitrary degree polynomial. Okay. Then we have some summaries. So this basically is some very important things we need to be very familiar with this in the future to use it. Okay. Bode plots first. Bode plot fundamentally is a picture representing the relationship of a transfer function magnitude and the phase angle. But then both the horizontal axis and vertical axis are, I would say it in this way. For magnitude body plot, both axes are in logarithm scale. Both magnitude and frequency are in logarithm scale. And there's also a slight difference in these two logarithms. The horizontal axis is just the pure log, a common logarithm. But vertical axis is not pure log. There is also a 20 multiplied by the logarithm. Okay. So using such kind of picture to represent the magnitude of a transfer function. And then the phase angle of a transfer function is also in the horizontal axis of frequency, but vertical axis is not in log scale. It's still a linear scale, but in degrees. There's a unit, which is actually degree. Usually the magnitude does not have a unit. If it's just a amplifying coefficient, it does not have a unit. Okay, so that's body plot. So in order to plot a body plot, we need to understand we need to have some agreement on some basic notes or labels we use. Okay, there is the discussion in the lecture notes about decibels. Okay, why we use decibels as the vertical axis scale. Okay. That means we're taking common logarithm first and then multiplied by 20. That's the definition of decibel. So let's say if the transfer function has a magnitude of, let's say, 10, okay, magnitude of 10, taking the logarithm would be 1. Common logarithm would be 1, and multiply by 20, that's going to be 20 dB. 20 dB. And if a magnitude of 100, taking logarithm, that would be 2. Multiplied by 20, that would be 40 dB. Okay? But then sometimes transfer functions, they have units. Okay? If a transfer function is not used to represent only the amplification coefficient, sometimes it could be used to represent some quantities with units. For example, sometimes transfer function could be used to represent impedance. This is also very often we use impedance. Sometimes it could be used to represent current or voltage. So for these quantities, They all have a unit. Impedance has a unit of ohm. Okay, current has a unit of ampere. Okay, voltage has a unit of volt. So how do we handle this when we draw their body plot? Okay, there's also the explanation for the decibels of quantities having units. We are basically have agreement that before taking the logarithm, this quantity need to be compared to a base quantity first. Okay, we call that as normalization. We need to do normalization first. So when you look at the body plot or magnitude of some quantities with units, you first need to normalize these quantities by taking division or comparison between this quantity and a base quantity. Okay? For example, if you're trying to plot a body plot in dB ohm, okay, the first example in dB ohm, then that means we're talking about something, the quantity, something as impedance. And then we take this impedance. For example, if this impedance is Z, in order to plot body plot, we need to compare this quantity with a base impedance. And base impedance, if we're talking about this dB ohm, that means we're using 1 ohm impedance as base impedance. So first, comparing to 1 ohm base impedance and taking the common logarithm and then multiply by 20. That's how much dB ohm that this quantity has. Okay. Another example in the lecture notes is about dB microamp. If you are drawing a body plot in the scale of dB microamp, what does that mean? Again, this is the dB in quantity in dB with unit. For dB with unit, we take the quantity. We're talking about microamp. That means this is the current. So we're talking about the one current. Okay, let's say Ix. And because we're talking about dB microamp, that means we're using 1 microamp as the base quantity. And you compare this current with 1 microamp. That comparison then is used to take logarithm and multiply by 20. Okay. So therefore, as if we're talking about 60 dB microamp, that means 6 dB greater than a base current of 1 microamp. 6 dB, let's see, divided by 20, that's going to be 3. So that means the log is 3. right? When the log is 3, that means the original quantity is 1,000 times. 1,000 times of the base current, base quantity is 1 microamp. So 1,000 times of 1 microamp, that's 1 milliamp. Okay. So this is the agreement about how to draw the Bode plot of transfer functions. So we have agreement on the scale of horizontal axis. We have agreement on the scale of vertical axis. And also we have to pay attention to whether the quantity we're looking at has a unit or not. This is also maybe a good time for you, especially for Chinese students, because you have, as I mentioned, Chinese language is probably the only language other than English that has the complete terminology system. So therefore, you have to always find out what is the corresponding terminology between English terminology and Chinese terminology, including all these different terminologies in electrical engineering, but also in terms of mathematics. Okay, in mathematics, how do we represent different terminologies in Chinese and in the corresponding English representation? Okay. Logarithm, exponential function, logarithm function, and so on, all different mathematical terminologies. There is also example, okay, because on this picture we also see, okay, the this representations of micro, let's see, milli, micro, okay, then there's a kilo, mega, giga. What happens after micro? There's nano, right? Femto. All these things you need to get familiar, okay? Because in Chinese we never really look into how is it pronounced in English. Okay, getting familiar with this. Now, some of the typical Bode plots we're looking at. First, it is about if a transfer function has the form of f to the power of n. That means frequency to the power of n. Then, if you take the, if you want to draw the Bode plot, the magnitude Bode plot has a picture like this. Okay, horizontal axis in log scale, and vertical axis in the dB scale. When n has different values, okay, then this curve of this transfer function magnitude Bode plot will be in different slope of a straight line. So very often students would be asking, so why do we always take so much trouble in using log scale? Okay, and the benefits of using log scale now is showing here. Because very often we will be dealing with a transfer function in the form of f frequency to the nth power. Very often we're going to deal with such kind of transfer function. And such kind of transfer function, if you draw their body plot in logarithm scale, it's going to be a straight line. Very simple. And this straight line will be having different slope when this power number n is different. Okay, so somebody say, well, why is it a straight line? Because if you take the log, common logarithm, that power number n is going to be moving to the out of the logarithm. So therefore, the vertical axis scale is proportional to the number of n. Okay, and then this log of the frequency is exactly the horizontal axis scale. Log of frequency is exactly the horizontal axis. So therefore, the body plot is exactly a straight line. Okay, that's one important thing, an important transfer function. The other important transfer function we're going to review a little bit is the single pole. Single pole very often can be obtained through a simple RC circuit. Okay. If you have a voltage source connecting with a resistor in series with a capacitor, okay, then when you, let's say, look at the voltage across the voltage source and look at the voltage across this capacitor and look at the transfer function from V1 to V2. And that transfer function, based on circuit theory, can be represented in this way. And if you rearrange it, it is represented as a single pole. Okay. The single pole is going to be located at, it can also be rearranged, okay, represented as in this normalized form, okay. Because in this normalized form, omega 0 is going to be exactly showing the location or the position of this pole, where the pole is located. Okay, and in this normalized form, omega 0 is exactly equal to 1 over RC. Okay, now that's the transfer function, single pole transfer function. But then how about its body plot? Okay, you can do, of course, based on the physical meaning, you would be able to calculate the magnitude of this transfer function. Okay, it's going to be for the transfer function to let s equals j omega, and then you do all this calculate the magnitude of this single pole transfer function. It's going to be finally in this form, and then taking the dB scale, you would be able to draw the body plot. Similarly, for the phase angle, okay, magnitude and phase angle, but in the end you can draw the where is it? This is going to be the exact body plot of the magnitude of single pole. Again, this is not good because it's a curve. We like straight line. So very often in control theory, we would simplify this and using two sections of straight lines, okay, to approximately represent this single pole. And these two sections of straight lines is going to be for low frequency. This is a flat straight line, this flat part. Okay, and for high frequency part, this is another straight line with another slope, using two sections of straight line to represent single pole. And that will make sense very simple, because then we can very often draw this by hand and to discuss the performance of this single pole. We'll get into a little bit more detail after the break. Okay, let's take a break.